All right, let's get right into it. When you look around, everything you see, everything you are, is all held together by invisible connections between tiny atoms. It's incredible. Today, we're going to pull back the curtain on how those connections actually happen with something called valence bond theory.
But first, check this out. It's a bit of a magic trick. You pour liquid oxygen near a powerful magnet, and look at that. It gets stuck, just hanging there in midair. But then you do the exact same thing with liquid nitrogen, which is chemically super similar, right? And it flows right on by like the magnet isn't even there. So what is going on with oxygen?
Well, the simple models of bonding you might remember, drawing dots and lines for Lewis structures, they're great for a start, but they totally fail to explain weird stuff like this. They can't tell us why molecules have the shapes they do or why they have certain energies. To really get what's happening, we've got to go deeper.
And this is where valence bond theory comes in. It completely changes how we think about a chemical bond. Forget simple lines. We're talking about a real physical interaction, an overlap between atoms.
So here's the big idea, the core concept. A covalent bond is literally the overlapping of atomic orbitals. You can think of an orbital as the little cloud of space where an electron likes to hang out. A bond forms when the electron clouds from two different atoms actually merge, sharing the same space. And when they each bring one electron to the party, that shared pair acts like a powerful glue, holding the two atoms together. And this is just so intuitive when you think about it. The more those orbitals overlap, the stronger that glue is going to be. Why? Because the shared electrons get to be attracted to both nuclei at the same time, which makes for a really stable, really strong connection. More overlap equals a stronger bond. Simple as that. This chart shows it perfectly. Picture two hydrogen atoms floating in space, far apart. Nothing's happening. As they drift closer, their electron clouds start to overlap. The attraction kicks in, and the energy of the whole system drops. It's getting more stable. But there's a sweet spot. If they get too close, their positive nuclei start repelling each other like magnets pushed the wrong way, and the energy shoots right back up. The whole thing becomes unstable. And for hydrogen, that perfect distance, that low-energy sweet spot, is precisely 74 picometers. A picometer is a trillionth of a meter. So we're talking about an unbelievably tiny, incredibly specific distance where the bond is as strong and stable as it can possibly be. It's not just a theory, it's a measured fact.
Okay, so atoms overlap their orbitals to connect. Got it. But it turns out there are two main ways they can do this. You can think of them as two fundamental types of handshakes that atoms use to form every covalent bond in the universe.
First up, we have the sigma bond. This is your classic, direct, head-on handshake. The orbitals overlap right along the imaginary line connecting the two atoms. This is the strongest kind of bond, and it's always the first one to form. In fact, every single bond you see in a molecule is, at its core, a sigma bond. It's the foundation.
Then you've got the pi bond. This one's different. It's more like a sideways high five. It only shows up after a sigma bond is already there. It's a side-by-side overlap that creates these electron clouds above and below the main connection, with a weird little dead zone, a node, right in the middle where there are no electrons.
So, just to lock it in, sigma is the head-on, super strong bond that forms first, right between the atoms. Pi is the side-by-side bond that comes second with electron clouds above and below. You only get pi bonds when you have double or triple bonds. So now we have our two main building blocks, sigma and pi. Let's see how they stack together to build, well, everything. The recipe is actually so simple. A single bond, that's just one sigma bond. Easy. A double bond, well, that's your foundational sigma bond plus one of those pi bonds. And a triple bond, you guessed it, one sigma bond plus 2 times 2 pi bonds. It's this beautifully simple logical system. All right, let's put this to the test with a real-world molecule. This is butadiene. It's a super important chemical for making synthetic rubber. So the challenge is, can we count up all the sigma and pi bonds hiding in there? Let's do it together. First, just remember that every connection contains one sigma bond, so count them up. There are 6 carbon-to-hydrogen single bonds and 1 carbon-to-carbon single bond. That's 7. Now look at the 2 double bonds. Each one of those also has a sigma bond, so that's 2 more. 7 plus 2 gives us 9 sigma bonds total. And what's left? Each double bond has 1 pi bond, so that's 2 pi bonds. 9 sigma, 2 pi. Done. Okay, so we know how bonds are built, but now for nuance. We often talk about bonds being either covalent, where electrons are shared, or ionic, where one atom steals an electron from another. But in reality, it's not so black and white. It's a spectrum.
And the source material puts this perfectly. It says many molecules are somewhere in the middle. The electrons are shared, but not equally, creating a permanent separation of charge, what we call a dipole. Hydrogen chloride is the perfect example. Chlorine is way more electronegative, which is just a fancy way of saying it's really greedy for electrons. So in the tug of war for that shared electron pair, chlorine pulls them closer, leaving it with a slight negative charge, and poor hydrogen with a slight positive charge. It's still a sharing bond, but it's lopsided. And here's the really cool part. This isn't just a vague idea. We can actually put a number on it. By doing some measurements, scientists figured out that the bond in HCl is about 83% covalent in character and 17% ionic. It's literally a hybrid, a beautiful mix of both types of bonding. So let's zoom out and look at the big picture. What does all of this give us? Why is valence bond theory so important? Well, because it moves us beyond just drawing lines on paper, it gives us a physical model based on the actual quantum shapes of orbitals and how they physically interact. It explains why bonds have the lengths and strengths they do, and ultimately, why molecules fold into the complex 3D shapes that determine everything about them. So if you're going to take away just a few things, make it these. 1. Bonds are just orbitals overlapping. 2. Sigma bonds are the direct foundational handshake. 3. Pi bonds are the side-on extras for multiple bonds. And 4, the sharing of electrons is almost never perfectly equal. It's a spectrum. At the end of the day, understanding this is everything. As the source material says, it's the very heart of chemistry itself. It's the fundamental mechanism that drives how our entire world is built and how it works. And that brings us back to that weird magnetic oxygen. Now, valence bond theory is amazing, but to fully solve that specific puzzle, you actually need the next level up called molecular orbital theory. It just goes to show there's always a deeper layer to explore. It makes you wonder, if all the matter around us is just built from these simple orbital handshakes, what other mysteries about our world can they help us unlock?